Yeah, I'm Martin McBriarty from Intermolecular here in San Jose. Intermolecular is a small company that's now part of a much bigger family. We're now part of EMD Performance Materials, which is one of the main business units of the EMD group, which also includes Millipore Sigma, which is where you might have seen this big M before. Yeah, so today I'm going to talk about some work from Intermolecular as well as some of my earlier work from Pacific Northwest National Lab, where we used two different kinds of top-down approaches to XAS analysis. And I'll talk about what that means in a second. So yeah, I'll start off by talking about some assumptions that we make when we analyze XAS spectra. And then I'll talk about two examples. One is an example from geochemistry, where we're looking at uranium incorporation in iron oxides and oxyhydroxide minerals. And then I'll discuss an example from our work at Intermolecular, where we were looking at ferroelectric materials for logic and memory. So first off, assumptions in XAS analysis. So this is probably familiar to a lot of us, the XAS equation, and our actual XAS spectrum that we measure and then that we subsequently model is a sum of these chi of k contributions for photoelectron scattering. And I won't focus on this, but I'll just mention that we've got some red terms. The terms in red here are parameters that we're typically allowing to relax when we're performing an XAS fit. I also want to thank Bruce for putting together this really nice introduction to XAS, which has a lot of great resources here. But yeah, so these red terms that we're focusing on include path degeneracy, which we often think of as coordination number within a shell, amplitude reduction factor, which is typically just a little bit less than 1, or at least it should be. Delta R, which is a difference in path length versus some theoretical path length R naught. Usually we're not thinking about the whole length as the variable, but rather some perturbation of that. Thermal disorder parameters. I should say that the thermal disorder parameter is often used to describe other kinds of disorder as well, not just thermal disorder, but it's just generally a broadening in the bond length distribution. And the binding energy offset parameter. And so when we are fitting an XAS spectrum, we're typically simulating a bunch of photoelectron scattering paths and then summing them together and then letting some of these parameters relax. So let's just take a hypothetical example for a uranyl cation. So this uranyl cation might be in solution, or it might be adsorbed to a mineral and with a little bit of perturbation to its structure. But sort of the main features of the uranyl cation is that you have a uranium in the middle, typically uranium-6. And then we've got these two oxygens in this trans-dioxo configuration that have relatively short bonds on the order of about 1.8 angstrom. And then we have 4 to 6 equatorial uranium oxygen bonds, which are typically much longer. And so if we wanted to fit this XAF spectrum that we would get from uranyl, then we would typically start off by defining 2 uranium oxygen coordination shells and then fitting them. And so in this case, I might say, well, we know that we only have 2 trans-dioxo bonds, but we have 4 to 6 equatorial bonds. So I've got 1 coordination number to fit. I've got 2 interatomic distances to fit. So 1 for this shell and 1 for the equatorial shell. I've got 2 disorder parameters as well as 1 binding energy offset. So that's 6 variable parameters. And we'll include multiple scattering contributions as well, because they're important to just properly describe scattering across this trans-dioxo configuration. And so what we'll get is a fit shown as the dotted line here, which is the sum of these different contributions: the contribution from the trans-dioxo oxygens, the contributions from the equatorial oxygens, as well as multiple scattering contributions. And you can see we end up with a pretty decent fit to this relatively simple structure. The problem is, if we have something that's a lot more complex than this, it can be hard to model this discretely with just a limited set of coordination shells and get any kind of useful information out of it. So what I just described is what I think of as a bottom-up approach to XAS analysis, where we start off by identifying some potential photoelectron scattering paths. Then, if we have to, we group those paths together into virtual coordination shells. And so these shells, if we have something like with really high symmetry, like an FCC metal, this is nice because we do have kind of true degeneracy for say 6 or 12 atoms that all have the same symmetry relationship to the absorbing atom. But oftentimes we're also just grouping similar paths, not identical paths, but just similar paths together, which ends up giving us a little bit of a distribution of bond lengths. And then that virtual path then, or that virtual shell, we'll call it, typically has a coordination number greater than 1. We'll calculate chi of k for each of those, and then we'll fit the experimental spectrum by relaxing these virtual shell parameters, and we'll end up getting bond lengths, coordination numbers, disorder, etc. But if we have relatively complex samples, we can't discretely fit every single interatomic interaction, so we end up with kind of coarse results that are averaged over a few similar paths. Alternatively, for more complex samples, we might want to try a top-down approach, where we start off by identifying a set of potential coordination structures, and then somehow we obtain the whole structures as well as the dynamics for those coordination structures. And I'll mention a few ways we'll do that shortly. Then we calculate chi of k for each individual atom. So we're not lumping shells together in virtual shells, but rather we're calculating chi of k individually. And then we sum all of those together, and then we fit the experimental spectrum as a weighted linear combination of whole structures. So in this case, we're not fitting individual bond lengths, we're not fitting coordination numbers, we're assuming that we know all of that from the beginning, and that we have a full spectrum for each potential component that makes up the sample. So we end up with very few parameters, but the accuracy of the fit is overall limited by the quality of whatever our structure and dynamics are that we've obtained perhaps from a simulation. So there are a few ways we can get this information. The sort of standalone solutions, I think, are using molecular dynamics, or better yet, ab initio molecular dynamics, or also called BFT&D. The problem is that these are typically very computationally expensive if you want to do it with high-level theory. So this is something that we did at PNNL using the Cascade supercomputer, and it takes a lot of resources to get these A and D simulations, but you end up with results that you can be pretty confident in terms of both structures and dynamics. But there are more ad hoc solutions as well. If you wanted to calculate static structure through one method, either we can get it from X-ray diffraction analysis, neutron diffraction analysis, or a DFT structural relaxation, we can get a static structure that way. But the dynamics are really important for XAS analysis at finite temperature. So we can get a disorder parameterization to experimental data, which is what I did in the second example that I'll show today. Or you can use phonon spectra calculations, which is something that we're experimenting with at Intermolecular. And so this is generally more accessible, but possibly a little bit less rigorous. So any questions before I move on?
Thanks, Martin. That's a really nice overview of the two perspectives. Any questions from anyone right now? All right, you should go ahead and continue, and everyone should type their questions into the group chat, and then I'll either repeat your question or call on you at the next break.
Okay, thank you. Yeah, and some things might be a little bit more clear after I go through some worked examples here. So back at PNNL during my postdoc with, I was working with Kevin Rosso primarily, but also had a lot of projects with Eugene Hilton there, who's on this call. We were interested in uranium contamination in soils because up at the Hanford site adjacent to PNNL, there are a lot of radionuclides in the groundwater there making their way towards the Columbia River, and we want to understand how those radionuclides interact with the soils that they're moving through. So the uranium interactions with iron oxyhydroxides is pretty important there because uranium is a common radioisotope, radiotoxic element, and iron oxides are pretty much everywhere. So uranium, when it's moving through the environment, is typically in this uranyl configuration that we discussed earlier. And it can be reducible to uranium-4 or uranium-5, which are typically insoluble through redox reactions with either an environment or with some environmental chemistry or with some mineral substrate. And so what this means is that the uranium cycle in groundwaters can actually interact with the iron cycle, where we have a lot of natural dissolution and reprecipitation and formation and transformation of a bunch of different iron oxide minerals. So based on the chemical conditions, acidity, basicity, whether there's carbonate in the system, we can get a lot of different iron oxides and oxyhydroxides. And this isn't even including any of the sulfides or sulfates or carbonates or anything else. Like there's the iron mineral chemistry is very rich. And if we introduce contaminants into this constantly fluctuating system, then we can actually end up with incorporation of contaminants into the structure of these iron oxides and oxyhydroxides. So if we understand the coordination environment of uranium in reacted samples, we can predict its stability in these samples, and we can get some idea of how mobile or immobile the uranium may be. So in these systems, however, they're usually pretty complex because we often have, in a sample of uranium reacted with an iron oxyhydroxide, we have multiple components. We have uranium that's been incorporated, which typically takes on a fairly symmetric octahedral coordination, but we also have adsorbed uranyl, which has this highly distorted, it's, I guess more generally, it's a bipyramidal structure where it can have 4, 5, or 6 equatorial oxygens, but it always has the short trans-diaxo bonds. So one way that we went about analyzing the XAF spectra for the uranium incorporated iron samples is by a linear combination fitting of both experimental and simulated spectra. And so here's how we do it. We start off with a spectrum that for the incorporated uranium, and it's very difficult to get an experimental spectrum with just one incorporated uranium coordination. So we calculate these with ab initio molecular dynamics. And so in this case, we've calculated the structure and dynamics for, say, in this case, it's uranium-5 in goethite. And then we have simulated all of the photoelectron scattering paths and sum them together to get this chi of k. So we have some fraction of this spectrum, and then we also have adsorbed uranyl, which we've measured separately. And if we sum these together and some weighted sum with variable phase fractions, we can end up with a pretty good fit to the experimental data. And I want to mention one clue that we have multiple coordination structures here is that the experimental data shown in black here has a much smaller amplitude envelope than either of the single component structures. And we can see that the single component structures are often out of phase with each other, where we have a trough here, we have a peak here, for example. So we could kind of guess just by looking at the experimental spectrum that we had some sort of a combination of multiple distinct waves to end up with this fit. And so our outcomes here are these phase fractions F. So we want to make sure our theory actually works first before we get too far into this. And so something that was done in our first paper on this by Sebastian Karasit et al. Was to simulate uraninite, which is a relatively straightforward structure, UO2. It's a very high symmetry structure. And so they did AAMD of uraninite at cryogenic temperature as well as room temperature. Compare that to nano-uraninite samples or XFs, experimental XF spectra from nano-uraninite. And they got great agreement between the experimental and simulated spectra. And we also see this strong temperature dependence. As we go to higher temperature, we expect higher thermal disorder. We expect a smaller XAFs amplitude, and we see all of that quite nicely. So we validated the method. Now we can go forward and actually start solving some problems in geochemistry. So we looked at some previously published XAFs spectra. And so in this first case, work from Mike Massey, and they had ferrohydrate, which they reacted with uranyl and iron-2 as a reducing agent to wind up with uranium incorporated in goethite. And they performed a bicarbonate extraction to try to remove some weakly adsorbed uranyl. And when we do our linear combination fit, we can see we get a pretty good agreement with the main features in the spectrum. Especially, we can especially see that in the Fourier transform. And in this fit, we found that about 57% of the uranium is in the 5+ state in the octahedral sites in the goethite structure. But still, we have a lot of adsorbed uranyl. We looked at another example prepared of uranium-5 and goethite prepared in a different way, this way by the reaction of uranium-6 with iron-2 chloride. And this also followed an acid extraction. And here we see even more adsorbed uranyl, although we can still identify U5 in the octahedral site. So it seems like a general trend that we found is that there always seems to be adsorbed uranyl. And I won't get into the reasons why in this talk, but I will say it's pretty much always there, whether it's adsorbed or possibly incorporated, not necessarily in the crystal structure, but possibly at grain boundaries within the crystallites in the mineral. For a second example here, we can talk about uranium incorporation in a mixed nano iron oxyhydroxide. So if you prepare, if you react ferrohydrate with iron 2 and uranium 6, but in the absence of carbonate, so if you perform it under a controlled atmospheric conditions, you end up with lepidocrosite instead of goethite, rather mostly lepidocrosite. Our XRD analysis suggested that we have over 90% of the samples lepidocrosite here, less than 10% of the sample is goethite. And then we wash these with pH 3 HCl to remove adsorbed uranyl. So now if we do our XAFS analysis of these uranium incorporated samples, we might guess that the uranium will be in this majority lepidocrosite phase, right? But it turns out that if we do our fits to simulated uranium 5 or uranium 6 in lepidocrosite, as well as adsorbed uranyl, we don't get any good agreement whatsoever. These are the best fits that we could get, and as you can see, they don't make any sense. However, if we did linear combination fitting using our AMD simulated goethite structures, we actually get great fits. In this case, when we have smaller amounts of uranium in the sample, about half of it is in the 5+ state in goethite. Looks like maybe we have a little bit of U6 in the goethite, as well as about 30% adsorbed uranyl, and we get a fantastic fit. If we have a bit more uranium, then the best fit that we get shows that some of that uranium 6 is in lepidocrosite instead of goethite, but still, most of the uranium is in goethite. And so we can confirm this with HADF-STEM imaging, where we can see these little bright dots in the goethite, which correspond to strongly scattering uranium atoms. And we see these in the goethite, but we don't really see these in the lepidocrosite. Maybe we see a few of them in the higher uranium concentration sample. But overall, we estimated that uranium is a little bit more than 18 times as likely to be found in goethite as it is in lepidocrosite, based on the phase fractions that we calculated from XAFS and the overall amounts of goethite in the sample versus lepidocrosite. So this is an interesting finding for the way that uranium partitions under reducing conditions into different minerals with the same chemistry but different structures, which we found out by top-down XAFS analysis. And then as a final example for top-down XAFS analysis in geochemistry, we want to talk about an XAFS mystery of uranium-6 incorporation in hematite. So this has been studied by XAFS for nearly 20 years now. And the first publication on this, Duff et al. Back in 2002, made uranium-6 in hematite, and they modeled this assuming that they had uranium-6 incorporated into hematite as an octahedral configuration with these bond lengths, 2.2 to 2.4 angstroms, which are a little bit long. About 10 years later, Eugene Ilton did a similar experiment, pretty much did the same kind of co-precipitation, but modeled it a little bit differently, assuming that they had both incorporated octahedral U6 as well as adsorbed uranyl, and they got a pretty good fit to their XAFS data. And then a couple years later, a group at Manchester, I think it was, did a different kind of experiment, aging ferrohydrite. So instead of doing co-precipitation experiment, they did an aging experiment, and they modeled their XAFS data as having incorporated uranyl within the structure of hematite. They had some sort of a quasi-uranyl-like configuration. So we've got these three totally different interpretations of what's happening when you have U6 in hematite, but the XAFS spectra are all almost completely the same. Aside from a little bit of a difference here in the Ilton et al. Data, which might have been because of a difference in the data extraction, you see like from Chi of about 6 on, it's pretty much exactly the same. So how did we get these tremendously different fits? And it all has to do with the starting assumptions in their bottom-up XAFS analysis. So this seemed like a good application of the top-down analysis. So we started off with putting uranium into an iron lattice site in hematite. And if you're putting in this 6+ cation, you have to compensate for that extra positive charge somehow. And so we do that by creating iron 3 vacancies. So in hematite, there's a lot of symmetry distinct iron sites relative to this central absorbing site here where the uranium is. So we've got one phase sharing site in dark purple here. We've got 3 edge sharing sites. We've got a few other corner sharing sites here. And it turns out that for our best fits to experimental data, we typically need not just one iron vacancy, but we need multiple iron vacancies. It looks like this uranium sits inside of a vacancy cluster. And every time we pull out another iron vacancy, we have to add in a few protons for charge compensation. We need to pull out that first iron in order to compensate for U6, but then once we pull out the second iron, we need to add in 3 protons to make up for the 3+ charge we just took out. So when we have these protonated vacancies in this hydrohematite-like structure, then we can end up getting pretty good fits. And in fact, the best fits that we get have this particular configuration where we've got these 2 corner sharing vacancies marked by asterisks here. I'll call it just a 2C configuration. We can get pretty good fits if we assume that we have some sort of 2C configuration vacancies as well as adsorbed uranyl. And so we show a couple of fits here. If we fit the Marshall et al. Data, then we can get about 44% adsorbed uranyl. And then the rest of it is in 2 different 2C configurations. We have some phase sharing vacancies. We have some bulk vacancies. So it looks like there's kind of a potentially a zoo of different vacancy structures that are surrounding the uranium in the hematite structure. Similarly, with the Ilton et al. Data, we got similar results. Also, our best fit here had a combination of 2C vacancies plus a phase sharing vacancy, as well as 2C vacancies plus some bulk nearby bulk vacancy. So what is it about this 2C structure, this double corner sharing vacancy structure? Well, in this structure, the two corner sharing sites are 180 degrees opposed relative to the uranium site. And what this means is that when we take out an iron 3 and we only partially protonate these vacancies, then the electrostatic interaction between the oxygen, which is coordinated to the uranium, and this vacancy is much weaker than it would be if you had an iron 3 in this site. And so this allows these 2 oxygen uranium bonds to contract a little bit. And what you end up with is a uranyl-like structure within hematite. And so what we think is that the need to be able to get this kind of uranyl-like structure is important for the incorporation of U6. If you have a reducing environment, U5 is much more flexible. It's much more likely to take an octahedral-like structure, which is similar to what iron takes in its own minerals. So that's why we get ready incorporation of U5 into goethite, for example. But we find that U6 doesn't incorporate as well into goethite, and we have a more recent paper demonstrating that. So this concludes the first section where we showed that AMD-informed XAFs top-down analysis enable us to look at defects and incorporated elements in iron oxyhydroxides with unprecedented detail. And this was work done at PNNL, use the EMSL facilities, particularly the Cascade supercomputer. Some of our original beamline work was done at GSE cars at the APS. And so with this, I'll be happy to take questions on part 1 of the talk.
That's very interesting, Martin. Thank you. Jacinto, you have a question?
Yeah. Thank you, Martin. I think this is quite interesting. My question is more on the practical part of building the database. Since you are using ab initio, do you need to make the structures quite large to get good reference, or could you round it up to like a few unit cells to get a good reference to build your library?
Yeah, so in this case, our structures had 80 atoms in a rhombohedral hematite unit cell, for example. I think the goethite and lepidocrosite structures were of a similar size. So I think a few dozen atoms is what we needed to get a decent dilution of one uranium atom in the structure.
Thank you.
Welcome.
I was really interested in the strong preference for incorporation into the goethite instead of the I'm going to get the name wrong, lepidocrosite. Had there been some intuition that that might be the case based on wet chemistry experiments or some such thing?
I can't speak for that myself as somebody who was relatively new to the uranium incorporation problems at the time. But I think it surprised all of us that the uranium went into the goethite instead of the lepidocrosite. To be honest, we had synthesized the lepidocrosite heavy sample by mistake. It wasn't really a parameter space we were planning to work in, but when we found the results, we found we discovered something pretty unusual. So maybe Eugene can speak more to the surprisingness of that, but we know we wouldn't have been able to figure it out without the XAS.
Okay. Matt, do you have a mic? Would you like to ask your question?
Sure. So if you do the XAS, I'm assuming you're using FEF to do XAS calculations with several different absorbing atoms in your clusters. But if you do that, FEF and any other calculation engine will give a different E0 value depending on the local environment, the chemistry of your absorbing atom that you select. This could be pretty big if for, say, uranium in an iron oxide or iron hydroxide versus a uranyl, where you have a very short bond, and that can give a pretty big impact on the E0 value that FEF assigns for that calculated structure. That means when you sum up the spectra, you might need to take that into account, especially for low K value, say below 5. How do you do that?
Well, so in this case, there's only one absorber in the whole structure. That's the one.
No, there is not. You're summing over at least, well, I mean, if you're doing top down, then you have thousands of absorbers, right?
Or scatterers, yeah.
No, absorbers.
Absorbers.
Otherwise, it's bottom up, right? If you have a handful of absorbers, you can do this bottom up. But if you're doing, in order to do top down, you're summing over thousands of absorbers, right?
So we have within a cluster a few dozen scattering paths. We have a few dozen coordinating atoms in what we would maybe classically call the first, second, third, so on shells. And so in each case, that would be calculating the phase shift from these different elements, but there's still only a single uranium absorber within the structure for which we're calculating all of these.
Oh, wait, you have a single absorber? How is that different from bottom up?
Well, the difference is that instead of having fit parameters for each individual shell, or we end up fixing everything. We end up fixing the interatomic distances, we fix the disorders. So it might just be maybe this is more of a semantic question. But how would you define top-down, Matt?
Well, I thought you said that you were calculating many scattering paths from many different absorbers and adding those together in order to take into account all of the different possible scattering paths.
Oh, I see. So
from a single atom or from a multiple of environments, it could be that multiplicity could be 1,000 different sites.
Yeah.
Right?
So each environment that we look at would be a different AAMD simulation. So we'd have a different supercell with a different coordination structure and different dynamics. And from each individual supercell, we'll calculate an XAS spectrum. And so from supercell to supercell, as you have different coordination structures on the uranium, then yes, you would expect a different or potentially a different delta E naught. And one detail that I didn't get into here is that we did actually allow the delta E naught as a fit parameter in our final linear combination fits, because the delta E naught not only as a real parameter of shifts in the binding energy, but also as kind of a fudge factor for strain on the lattice, because that's one thing we didn't allow to change. If we're not allowing our interatomic distances to change, then the delta E naught actually acts as kind of an ad hoc strain parameter, because it causes sort of an accordioning of the entire spectrum. So we calculated each spectrum with delta E naught delta E naught steps of 2 EV and did it fit that way. So I think we did in some ways account for that.
Okay.
Thank you. All right, a couple more short, quick questions I'll read. Uranil has a shoulder in the Zanes at the higher energy of the main peak. Is that seen in the uranil-like materials that you studied for the bulk?
In the Zane, so I really don't recall if that uranil-like comp was seen there. Considering that about half of the uranium in these structures was adsorbed uranium, I think we did, but I'm not quite sure. I'd say check out the SI in the publications.
Okay, checking the SI, got it. Another question is, how would the protonation of the inner bulk actually occur? It says you had protonated the inner bulk to charge balance and was curious if that was a computational fix or if there was good reason to believe that that was the real solution to the situation.
Sure. So when you have precipitation of iron oxides in real natural environments in water, then we might expect that you would actually have some protonation or some incorporated protonation some way or another. You'd end up with hydroxyl groups. This has been studied a little bit as hydrohematite, or low temperature or hydrothermally grown hematite, as opposed to, say, hematite that's been sintered at 1200 C or something like that, where you might expect to remove all of the water or water-related species like hydroxyl groups. Real iron oxides formed under real environmental conditions are probably loaded with these kinds of defects.
Got it. Okay. Last question was whether you had done any uranium M4 edge HERFD, for example, to confirm the presence of the uranium-6.
That was the dream. We weren't able to actually do that, but we would have loved to.
Okay.
We really enjoyed that work, the Kashnin et al. Work, especially in their the ability to distinguish U4, 5, and 6. You know, U5 has been a major interest of Eugene's for a long time, and so that work was quite exciting to read, but we were never able to do it ourselves.
Okay. All right.
Just at this point, this is Eugene Hilton from PNL, that we have confirmed the presence of uranium-5 using XPS and the presence of uranium-6 using XPS in the same sample. But of course, the XPS is not telling us exactly where the uranium-5 or the uranium-6 is.
Okay. All right. Well, thank you. You should continue, Martin. This is fascinating.
All right, thank you. And I think this last bit will be a little bit shorter. So here I'll be looking at, instead of looking at defects, I'll be looking at bulk structures using this method or using a related method. So at Intermolecular, we've been interested in ferroelectric oxides for a while. These are going to be useful in a lot of emerging logic and memory applications, including these so-called negative capacitance field effect transistors, where we have coupling between a ferroelectric and a standard dielectric to actually reduce the switching speed of, or I guess increase the switching speed, reduce the switching time of transistors. But there's lots of other potential applications as well. But one of the challenges has been to come up with some sort of a CMOS compatible process for depositing some kind of ferroelectric that can work with silicon, that will work with silicon oxide, et cetera. And so at Intermolecular, we've developed ALD processes for hafnium oxide and zirconium oxide, the blend of which is a really good CMOS compatible ferroelectric. So this material system has been interesting to us for a while. We've published a little bit on it over the past few years. This is one example where we made these angstrom precise multi-layers of hafnium oxide and zirconium oxide and compared their ferroelectric behavior to hafnium oxide, zirconium oxide alloys. I should say that hafnium and zirconium oxide are very similar materials. They have similar lattice parameters, similar structures, but their main difference is in their phase stability. There's a lot of different quasi-fluorite-like crystal phases that hafnium oxide and zirconium oxide can take under different conditions and under different sizes, which I'll show in a second. But that just gives a broad overview of why we're working with these materials. But anyway, so we've grown these multi-layers. And so these are 8 nanometer thick films total. So in this case, we've got 1 nanometer of hafnium oxide, 1 nanometer of zirconium oxide, et cetera. In this case, we've got 2 nanometer films. In this case, we have just a sandwich of 2 4 nanometer films. And we look at their ferroelectric performance, looking at their polarization curves. And we see that the film that has these 1 nanometer hafnium oxide and zirconium oxide layers, that is, has the most interfaces built in, has the largest ferroelectric polarization, the largest remnant polarization here, which is our kind of main ferroelectric figure of merit. And so, yeah, if we look at the layer thickness here for the hafnium zirconium oxide alloy, we have a reasonable ferroelectric polarization, but it's much, much better when we have this interface-rich nanolaminate. And so we know that interface effects must be at play here. It must be something about these interfaces that's improving the ferroelectric performance. Whether it has to do with the way that we have strain fields from the substrate that might be amplified or mitigated by the underlying layer. We know that crystal phase stability is strongly dependent on the thickness of the film, so that could be a contribution as well. But there's still a lot to be learned about how interfaces actually modify the crystal phase stability of hafnium zirconium oxides. And part of that is that it really depends not only on the thickness, but also the chemistry and the stoichiometry of the film. So if we look at the range of compositions between hafnium oxide and zirconium oxide, when we have a hafnium oxide rich film, we typically get a monoclinic phase, which is also the most stable phase for bulk hafnium oxide and bulk zirconium oxide at room temperature and standard pressure. But this is paraelectric. It doesn't have any interesting ferroelectric properties, although it also makes a great high K dielectric, and it's being used for that right now. As we start to include zirconium in the structure, once we get to about half and half hafnium oxide and zirconium oxide, we end up with this orthorhombic phase, which is non-centrosymmetric and demonstrates ferroelectric behavior. And this is the polarization curve for this composition, and here we see a nice ferroelectric loop. When we get more zirconium rich, we end up getting this anti-ferroelectric-like behavior, where we have a pinched ferroelectric curve at zero field, but we have some ferroelectric behavior at higher field. And this is characteristic of the tetragonal phase of zirconium oxide, which is actually of interest for use as a dielectric as well, and is being used, or at least considered for use in things like DRAM. So if we wanted to understand or predict the performance of hafnium oxide and zirconium oxide films under, say, different processing conditions, doing different, depositing different thicknesses, if we wanted to be able to predict their properties in a high throughput way without having to make devices every time, then it would be nice to have some sort of a signature of the orthorhombic ferroelectric phase, so we would know whether a sample is going to show good ferroelectricity or not. The problem is that the ferroelectric phase and the tetragonal phase have very similar long-range order, and they have very similar diffraction patterns as a result. The monoclinic phase is pretty easy to distinguish, but we have a couple of features here that we can use to distinguish the orthorhombic phase. But when we have real nanoscale films, by XRD, we can't see any of those. The peaks are broader, weaker, and it obscures these important features. So throughout the rest of this talk, I'm going to focus on these two structures. One of them is I'll call sample SCH, which has our silicon substrate, then 3 nanometers of zirconium oxide, and then 3 nanometers of hafnium oxide, so silicon, zirconium, hafnium. And then the opposite configuration of hafnium zirconium oxide, where we have the hafnium oxide sandwiched between zirconium oxide, which has a free surface, and the silicon substrate. So how else can we distinguish their phases? Well, you might have guessed, since this is the XAS Journal Club, that these have pretty similar diffraction patterns, but much different local structures that we can tell apart by XAFs. The monoclinic and orthorhombic ferroelectric phase both have this 7-fold metal-oxygen coordination, where each bond has a different bond length. Then we also have a much higher symmetry tetragonal coordination, where we have 8-fold metal-oxygen coordination, but we only have 2 sets of bond lengths. We have 4 short bonds and 4 long bonds. And so what that means is that if we simulate the XAFs for these different structures, then the monoclinic and orthorhombic are pretty similar, but the tetragonal is quite distinct. And so our top-down solution here for distinguishing the different crystal phases in hafnium oxide and zirconium oxide is to start with a static crystal structure. So we got these from either diffraction or DFT. Then we needed to parameterize the thermal disorder somehow, because in this case, we didn't have access to a National Lab supercomputer, so we couldn't do AAMD. We needed something a little bit simpler. Then once we have the static crystal structure and the thermal disorder, we could simulate the XAFs and then perform linear combination fitting to figure out the crystal phase fractions within these bilayers. So we wanted to look at how much of each of these crystal phases do we have for each material, that's hafnium oxide and zirconium oxide. So that's 6 different phases we want to be able to pick out. 3 from the hafnium L3 edge and 3 from the zirconium K edge. So we were able to simulate all of these different XAF spectra. And the way that we got our thermal disorder was just through this really simple linear parameterization, with the assumption that the disorder parameter would get larger as we went to higher R. We just had this linear parameterization with A and B here, which we fit to experimental spectra. So for hafnium oxide, we had monoclinic hafnium oxide film that we were able to get an XAF spectrum from, and then we fit these parameters to get a good agreement between our simulated spectrum and this experimental spectrum. Same with zirconium oxide, where we actually fit to tetragonal and monoclinic structures. And together we ended up with these parameters for A and B. We also were able to get the S0 squared here, which is in both cases a little bit less than 1, which is physically reasonable. And we can look at their Fourier transforms as well, and we see good agreement there. Yeah, one thing I want to mention is that with the tetragonal case, because we have these 2 different sets of bonds, when we had 4 short bonds and 4 long bonds, in the hafnium oxide case, which we've simulated by a DFT, there's pretty good separation between the short bonds and the long bonds. So you end up with this nice broad peak. Oh, sorry, I think it might have been actually much less separation. So we end up with a peak where we can, which sums the 2 nicely. With zirconium oxide, we actually have a bit more separation between the short bonds and the long bonds. And we end up with destructive interference in the Fourier transform, which gives us actually very little magnitude in the Fourier transform. So this is a great example, I think, of how your Fourier transform is not a radial distribution function because of interference effects, and that's glaringly obvious in this case. So now we actually perform some linear combination fits. In the case of the sample SZH here with zirconium in the middle, we only got 1 really good fit. And so in this case, we were doing pretty much every permutation of monoclinic only, orthorhombic only, monoclinic plus orthorhombic, monoclinic, orthorhombic, and tetragonal all together. And then we were evaluating which fits looked reasonable and which didn't based on, I think it was based on the R factors in the fits. And so we found the best possible R factor, and then we only considered fits within, I think, 25% of that best possible R factor. So there's only 1 good fit for zirconium in the SZH stack. We had 2 pretty good fits for zirconium in the SHZ stack. And so if we propagate the results from these 2 fits, as well as with some assumed error, then we can end up with these phase fraction ranges here for zirconium oxide. And we can see that they're fairly tight. I mean, it's we're typically plus minus 9% at best, but it's not too bad. And we can see some difference here. We can see a significant difference between the sample SZH with zirconium in the middle versus zirconium on top of the stack. When the zirconium is on top of the stack, we end up with a much higher orthorhombic phase fraction. So we might suspect that this sample would have better ferroelectric performance. The story is a little bit less clear for hafnium, because with hafnium oxide, the monoclinic and orthorhombic spectra are much more similar than they are for zirconium oxide. And so in this case, we got 2 pretty good fits for sample SHC, but these 2 fits ended up giving us a pretty broad range of potential phase fractions. So there's this huge uncertainty just from the XAFs alone. But if we remember from our XRD, we actually had a really nice distinction of monoclinic from the orthorhombic and tetragonal. So we wrote a script, which I should mention used Matt's lmfit Python code in order to fit our diffraction peaks here. And we could end up getting a more precise measurement of the phase fraction of monoclinic. And so when we fit that together, when we calculate using combination of our phase fractions from XAS and our phase fractions from XRD, we can solve for the monoclinic phase fraction and by extension the orthorhombic phase fraction and end up with a much smaller uncertainty range here for these broadly uncertain hafnium oxide phase fractions. And here we can see that the hafnium oxide phase fractions actually don't depend as much on the stacking order here. So whether the hafnium oxide's in the middle of this sandwich and constrained by these two interfaces, or whether it's on the very surface and only constrained by the bottom interface, we end up with pretty similar phase fractions. So what insight does this actually give us into engineering ferroelectrics? Well, one thing that we knew ahead of time from the literature is that zirconium oxide tends to crystallize much more readily at lower temperature than hafnium oxide. And it's been also suggested that having a higher density of randomly oriented crystallites will favor the orthorhombic ferroelectric phase. So what we think is happening is that when we anneal with a free zirconium oxide surface, that is in sample SHZ, that we end up with a higher orthorhombic phase fraction because we have this unconstrained surface, which enables, somehow enables the formation of orthorhombic phase. And when we deposit the same stacks on top of titanium nitride as a bottom electrode, and then we add top electrodes and do a ferroelectric polarization measurement, we do in fact see that the zirconium oxide case has a much larger ferroelectric polarization than the case with zirconium oxide sandwiched in between the tinitride and hafnium oxide. So here we've shown a new way to distinguish the crystal phases of hafnium oxide and zirconium oxide, which we couldn't do just by XRD alone. Before I finish, I just want to talk a little bit about Intermolecular and who we are and what we do. We are a high throughput thin film facility. We've got a pretty big fab on our site in San Jose, which we have just brought back up since it turns out that the semiconductor industry is considered essential right now. So we've got our fab running at limited capacity, but we have a lot of PVD chambers, ALD chambers all running 300 millimeter silicon wafer. These are 300 millimeter silicon wafer tools, just as are used in fabs. So we specialize in combinatorial methods, high throughput methods, and particularly we have worked a lot in the memory space. So for emerging memories like phase change RAM, we've been doing some chalcogenide ALD work. Have historically been interested in ReRAM as well. So if you're interested in these subjects, we're always interested in talking about potential academic collaborations. So please be in touch if you're curious about what we do. But yeah, with that, I'll finish off and thank you very much for your attention.
Thank you, Martin. That was that's terrific. We've got a bunch of questions for you. We'll start with Jacinto.
Hi, Martin. You touched a little bit on this aspect of not being able to calculate all the structures with for the thermal parameter. Is it, and Jens kind of briefly replied to this to me, but is it possible that you would calculate the fingerprint at let's say low temperature and then let this parameter float to get a better fitting and get this from the fitting, or do you think you need really to calculate fingerprints at least with several thermal parameters to get a good fitting?
So there's probably a more straightforward way to do this. If we go back and look at the XAS equation, we could probably have a relatively quick way to just modify the thermal disorder parameters in some logical way. I mean, if we have dozens of atoms in our cluster and we're letting all of our thermal disorder parameters vary wildly then without any sort of relationship between them, then we could end up having some issues. But it also turns out that there are some cases where the thermal disorder parameters don't have a fairly straightforward relationship from one to the other. So there's some evidence that in some phases of zirconium oxide and hafnium oxide, for example, that some disorder parameters are much larger than others within the same, what we might consider to be the same coordination shell. So I think there's a lot of different ways to do it. We just picked a way that was simple and straightforward and ended up giving us really good quantitative agreement with with experiment, but I'd say I'd love to hear and see other ways to do it.
Okay. Peter, are you there?
I am. I'm sorry, I'll go back to the urinal question with the shoulder a little bit. As in our paper, in the Marshall paper, we did see a shoulder within the veins of the urinal-like species, except that the shoulder moved to lower energy, that it was almost completely merged with the white line. Now I've got one question, and that's, I'm always really interested in using ab initio molecular dynamics or molecular dynamics in fitting very complex XAS spectra, and specifically for environmental engineering. And because I'm not a computational chemist, I was wondering if you could give some tips on where and how to start with this kind of computations.
Mm-hmm. So to your first point, I think there has been a clear established relationship between the bond lengths of the trans-dioxo uranyl bonds and the position of the shoulder just above the white line for uranyl. And
yes, that's why I was almost completely merged with the white line.
Right, and I think
paper,
it's possible that there's that there are multiple components there. I think this is something that Eugene and I had looked at, where if you are summing together, say, aqueous-like uranyl, which would be the absorbed case, and the incorporated like uranyl, that you might end up kind of, I think they might end up kind of dampening each other out, but I don't recall exactly what we concluded there, so I won't go any further into that.
I can only recall what we concluded in the Marshall et al. Paper.
Okay.
So, but we think we saw the shoulder almost completely merged with the white line, so it moved to quite a couple EV lowest energy in the same.
Yeah, and that would correspond to, I think that corresponds to a longer and weaker trans-dioxo-uranyl bond. So I think our works are fairly in agreement there.
Yeah.
But and then as for learning to do computational chemistry in AMD, I think there are a lot of free packages out there. Like I want to say for classical MD, something like LAMPS maybe might be free, but I really don't remember. We were using NW Chem for all of this, which I believe is also freely available. But for the ab initio molecular dynamics, you really need some very powerful computational tools. But I think it's worthwhile to start experimenting with classical molecular dynamics and see if you can reproduce some, say, you can just reproduce like the average static structures from XRD or something like that, and build up from there. But I'm not sure where exactly I would start.
Thanks.
All right, we have a question. How are you constraining the phase fractions of the, for example, the monoclinic phase and the LCF calculations for the SZH and SHZ, especially with respect to XRD?
I see. So in the actual linear combination fits, I'm not constraining the phase fractions. I'm only constraining that they sum to 1. So that's after I get the S0 squared from the original thermal disorder parameterization. Then I can assume that if I include that S0 squared in the simulation for each in the simulation of each spectrum, that then when I do a linear combination fit, all of the phase fractions should sum to 1. So I have that fixed. I'm using Athena for this, by the way. So the in this table, I'm just showing the phase fraction ranges that we get from our linear combination fits. And whenever I do the constraining with the XRD, I have a separate series of equations set up, which are in the SI of this paper. So you can refer to that if you'd like. But in this case, I think I just used the phase fractions from, I used the phase fractions from all the zirconium oxide phases in the T hafnium oxide. But then I just ignored the phase fractions from the XAFs for the hafnium oxide, and I used instead the phase fraction for the monoclinic hafnium oxide. Actually, I'm sorry, I might have misspoken here. I think I actually had used the fitted XRD intensity. Sorry, yeah, it solved for the monoclinic hafnium oxide intensity separately here. I'd say, yeah, refer to the SI in this paper. It's open access. It's really available for details on how we did this combination of XAFs and XRD phases.
Okay, there's a related question for the XAFs of SCH and SHZ. Is it in plane or out of plane measurement, and is there any polarization dependence?
We did not measure polarization dependence. And yeah, to be honest, I wasn't present for the experiments, so okay. I can't comment on that. But we did not do polarization dependent XAFs.
All right. Last question, Jens, are you there?
Yep. Very short. When you start to fit or top down, you have so many different model parameters, and you say you left your E naught and other parameters free. You're coming in the range when you have where you might potentially have multiple minimas. How do you address this? How do you approach this?
So with the top-down approach, you typically don't actually have too many fit parameters. What you do have, though, is potentially a very large basis of different structures. And so in the case of the uranium incorporation in hematite, for example, if you check out our paper on that, you'll see we had a lot of different vacancy configurations that we studied. I mean, there's probably about a dozen different vacancy configurations. And so we ran linear combination fits with lots of different combinations of those. And we found that there was not really degeneracy, but some of the fits were quite close to each other in terms of their the overall quality of fit. And that's because some of the structures were quite close and quite similar to each other. So from there, we came up with a feasible model for which vacancy configurations we might have, but we weren't too strong on our conclusions about what exactly vacancy configuration it was. But what each of these best fits shared was that we had this double corner sharing vacancy configuration. And so we thought that was a much more clear result. But yeah, in terms of the parameters that we have to modify, because we're starting off with fixed structures and fixed disorders for every path, the main variables that we have are the phase fractions for each individual fit. Although we do a whole ensemble of fits, we only select the best fits to move forward with in our analysis, as well as the binding energy offsets, as we talked about with Matt a little bit earlier.
All right. Martin, thank you. It was a wonderful talk. Thank you for everyone for coming and for your questions.